Welcome back to the channel. Today, we are going to take a slow, gentle walk through the strange but very real world of quantum physics, how tiny particles behave, how they give rise to the world we see, and how new technologies, like quantum computers, grow from these ideas. If you enjoy learning in this quiet, long-form way, please remember to like the video, subscribe to the channel, and share it with someone who might fall asleep to science just like you. Thank you so much for being here. I am very curious. What time are you listening to this, and where are you right now? Let me know in the comments so we can see how this little community is spread across the world. In everyday life, the world appears stable and predictable. A ball rolls across a flat floor and slows down in a steady way. A cup rests on a table and stays where it is placed. A car moves along a road, accelerates when the driver presses the pedal, and comes to a stop when the brakes act on it. These motions can be timed with a simple clock and measured with a ruler. When the same situation is recreated carefully, the results repeat in a dependable fashion. This familiar reliability is the starting point for any description of nature in physics. At this scale, objects have well-defined positions and speeds at each moment in time. A point on a wheel can be tracked as it turns. A stone thrown into the air follows a smooth arc that can be followed with the eyes. If two stones are thrown with the same strength and in the same direction, they land in almost the same place. If the throw is repeated many times, under carefully controlled conditions, the small differences remain minor. Even when there is some variation, it is usually clear that it comes from slight changes in the starting conditions or from small influences, such as air currents. Classical physics is the name given to the set of ideas that describe this familiar world. It includes the laws of motion first written clearly by Isaac Newton and later refined, as well as the laws of electricity, magnetism, and heat. In classical physics, objects are described by their positions, their speeds, and the forces acting on them. These quantities are treated as sharp and well-defined at each instant. If the position and speed at one moment are known precisely, and the forces are also known, the future motion can be calculated in principle with great accuracy. This view of nature is often called deterministic. In such a picture, probability is used only when there is incomplete information, or when it is not practical to track every detail. For example, the path of each air molecule in a warm room is far too complex to follow. But the average pressure and temperature of the gas can be predicted and measured. The point, however, is that the molecules themselves are assumed to follow definite paths, even if those paths are unknown in practice. To make these ideas concrete, it is useful to think about simple measuring devices. A wooden ruler has marks set at regular distances along its length. A length measured with this ruler is given a definite value, such as a certain number of centimeters. A mechanical clock has a hand that sweeps around a dial or a pendulum that swings back and forth. The regular motion of the hand or the pendulum defines equal intervals of time. If a ball rolls along a track and passes two marks that are a fixed distance apart, the time between the crossings can be read from the clock, and the speed can be calculated by dividing the distance by the time taken. Repeating the experiment gives consistent results if the setup is stable and the instruments are functioning properly. This close link between measurement and prediction is a key feature of physics at everyday scales. Another example is a simple balance scale. Two pans hang from a beam that can tilt. When equal masses are placed in the pans, the beam balances horizontally. If a known mass is placed in one pan and an unknown mass in the other, the tilt of the beam shows which is heavier. By adjusting the known mass until the beam balances, the mass of the unknown object is determined. The result is a single, well-defined number. If the procedure is repeated, the same number is obtained within a small margin of error. The small differences, when they occur, are attributed to imperfections in the apparatus or in the way it is used. Over time, improvements in engineering have made instruments more sensitive and more reliable. Metal rulers expand and contract only slightly with temperature and carry carefully engraved marks. Precision clocks use steady vibrations of crystals to keep time. Thermometers use liquids or electronic sensors that respond in a stable way to changes in temperature. When these instruments are calibrated against standard references, they allow measurements to be compared from one laboratory to another. A length measured in one place means the same as the same length measured elsewhere. A second of time marked in one clock matches a second marked anywhere else that uses the same standard. These shared standards form the backbone of large experiments, industrial processes, and navigation systems. At this stage, the world seems to be fully described by sharp quantities and smooth changes. If a measuring device is made more accurate, it is expected to reveal more detail while still fitting into the same framework. A better ruler gives more decimal places for a length. A better clock divides time into finer steps. In each case, the underlying assumption is that the object being measured has a definite length or a definite time of motion, and the instrument is simply approaching that value more closely. When scientists push this pattern of careful measurement to smaller scales, they start with the same expectations. If a microscope reveals the structure of a grain of salt, it shows tiny crystals with well-defined shapes. Under higher magnification, smaller features appear, but they still seem to have clear positions and sizes. In early work on atoms, many researchers expected that with better tools and more refined methods, every part of an atom would eventually be described in the same clear way as the parts of a machine. The picture is one of gears, orbits, and trajectories all behaving according to the same deterministic rules. It is important to note that even within classical physics, there is room for complex and chaotic motion. A turbulent stream of water, a weather system in the atmosphere, or the motion of three or more bodies under gravity can be extremely sensitive to small changes in initial conditions. In these cases, long-term prediction becomes very difficult. Still, at any instant, each part of the system is assumed to have a definite position and speed, and the laws governing the motion are clear. The difficulty lies in tracking the details, not in any limitation of the basic framework. Across many branches of engineering and applied science, this approach has been enormously successful. Bridges stay standing when designed with the classical laws of forces and stresses. Planets move in their predicted orbits for decades and centuries. Electrical circuits in homes and devices can be designed and analyzed using classical rules for currents and voltages. Measurements agree with these predictions to a high degree of accuracy, especially at scales far larger than atoms and molecules. This success supports the idea that nature, at least in the familiar range of sizes and energies, is well captured by continuous quantities that can be measured as precisely as instruments allow. In such a world, The role of a measuring device is straightforward. It reveals values that already exist, at least in principle, before the measurement is made. A thermometer shows the temperature that the air already has. A scale shows the mass that an object already has. A ruler shows the length that a table already has. This quiet picture of reality, in which properties are present with definite values and measurements, simply uncover them more clearly, forms the outer setting in which deeper questions about matter and light are asked in modern physics. In everyday life, the world appears stable and predictable. A ball rolls across a flat floor and slows down in a steady way. A cup rests on a table and stays where it is placed. A car moves along a road, accelerates when the driver presses the pedal, and comes to a stop when the brakes act on it. These motions can be timed with a simple clock and measured with a ruler. When the same situation is recreated carefully, the results repeat in a dependable fashion. This familiar reliability is the starting point for any description of nature in physics. At this scale, objects have well-defined positions and speeds at each moment in time. A point on a wheel can be tracked as it turns. A stone thrown into the air follows a smooth arc that can be followed with the eyes. If two stones are thrown with the same strength and in the same direction, they land in almost the same place. If the throw is repeated many times under carefully controlled conditions, the small differences remain minor. Even when there is some variation, it is usually clear that it comes from slight changes in the starting conditions or from small influences such as air currents. Classical physics is the name given to the set of ideas that describe this familiar world. It includes the laws of motion first written clearly by Isaac Newton and later refined, as well as the laws of electricity, magnetism, and heat. In classical physics, objects are described by their positions, their speeds, and the forces acting on them. These quantities are treated as sharp and well-defined at each instant. If the position and speed at one moment are known precisely, and the forces are also known, the future motion can be calculated in principle with great accuracy. This view of nature is often called deterministic. In such a picture, probability is used only when there is incomplete information or when it is not practical to track every detail. For example, the path of each air molecule in a warm room is far too complex to follow, but the average pressure and temperature of the gas can be predicted and measured. The point, however, is that the molecules themselves are assumed to follow definite paths, even if those paths are unknown in practice. To make these ideas concrete, it is useful to think about simple measuring devices. A wooden ruler has marks set at regular distances along its length. A length measured with this ruler is given a definite value, such as a certain number of centimeters. A mechanical clock has a hand that sweeps around a dial or a pendulum that swings back and forth. The regular motion of the hand or the pendulum defines equal intervals of time. If a ball rolls along a track and passes two marks that are a fixed distance apart, the time between the crossings can be read from the clock, and the speed can be calculated by dividing the distance by the time taken. Repeating the experiment gives consistent results if the setup is stable and the instruments are functioning properly. This close link between measurement and prediction is a key feature of physics at everyday scales. Another example is a simple balance scale. Two pans hang from a beam that can tilt. When equal masses are placed in the pans, the beam balances horizontally. If a known mass is placed in one pan and an unknown mass in the other, the tilt of the beam shows which is heavier. By adjusting the known mass until the beam balances the mass of the unknown object is determined, the result is a single well-defined number. If the procedure is repeated, the same number is obtained within a small margin of error. The small differences when they occur are attributed to imperfections in the apparatus or in the way it is used. Over time, improvements in engineering have made instruments more sensitive and more reliable. Metal rulers expand and contract only slightly with temperature and carry carefully engraved marks. Precision clocks use steady vibrations of crystals to keep time. Thermometers use liquids or electronic sensors that respond in a stable way to changes in temperature. When these instruments are calibrated against standard references, they allow measurements to be compared from one laboratory to another. A length measured in one place means the same as the same length measured elsewhere. A second of time marked in one clock matches a second marked anywhere else that uses the same standard. These shared standards form the backbone of large experiments, industrial processes, and navigation systems. At this stage, the world seems to be fully described by sharp quantities and smooth changes. If a measuring device is made more accurate, it is expected to reveal more detail while still fitting into the same framework. A better ruler gives more decimal places for a length. A better clock divides time into finer steps. In each case, the underlying assumption is that the object being measured has a definite length or a definite time of motion, and the instrument is simply approaching that value more closely. When scientists push this pattern of careful measurement to smaller scales, they start with the same expectations. If a microscope reveals the structure of a grain of salt, it shows tiny crystals with well-defined shapes. Under higher magnification, smaller features appear, but they still seem to have clear positions and sizes. In early work on atoms, many researchers expected that with better tools and more refined methods, every part of an atom would eventually be described in the same clear way as the parts of a machine. The picture is one of gears, orbits, and trajectories all behaving according to the same deterministic rules. It is important to note that even within classical physics, there is room for complex and chaotic motion. A turbulent stream of water, a weather system in the atmosphere, or the motion of three or more bodies under gravity can be extremely sensitive to small changes in initial conditions. In these cases, long-term prediction becomes very difficult. Still, at any instant, each part of the system is assumed to have a definite position and speed, and the laws governing the motion are clear. The difficulty lies in tracking the details, not in any limitation of the basic framework. Across many branches of engineering and applied science, this approach has been enormously successful. Bridges stay standing when designed with the classical laws of forces and stresses. Planets move in their predicted orbits for decades and centuries. Electrical circuits in homes and devices can be designed and analyzed using classical rules for currents and voltages. Measurements agree with these predictions to a high degree of accuracy, especially at scales far larger than atoms and molecules. This success supports the idea that nature, at least in the familiar range of sizes and energies, is well captured by continuous quantities that can be measured as precisely as instruments allow. In such a world, the role of a measuring device is straightforward. It reveals values that already exist, at least in principle, before the measurement is made. A thermometer shows the temperature that the air already has. A scale shows the mass that an object already has. A ruler shows the length that a table already has. This quiet picture of reality, in which properties are present with definite values and measurements, simply uncover them more clearly, forms the outer setting in which deeper questions about matter and light are asked in modern physics. As instruments grow more sensitive and conditions inside the laboratory become more carefully controlled, a change appears in the way certain phenomena are recorded. Instead of smooth traces and continuous motions, many measuring devices begin to respond in sudden, separate steps. A detector connected to a loudspeaker produces distinct clicks rather than a steady hiss. A screen designed to show the impact of incoming particles lights up in isolated flashes, each one confined to a small region. A digital counter advances and jumps, moving from one whole number to the next as events occur. In these settings, the flow of light or particles reveals itself not as a continuous stream, but as a sequence of individual arrivals. One clear way to see this behavior is to consider a very faint beam of light directed at a sensitive detector. When the beam is bright, the detector output looks almost continuous, as if a constant signal is being delivered. If the intensity is slowly reduced, however, the signal changes character. At intermediate levels, it becomes grainy, and at the lowest levels, it consists of sharp, separated pulses. Each pulse marks a moment when the detector registers that light has been absorbed. On a display, these pulses appear as spikes. Through a loudspeaker, they become clicks. If the beam is kept steady in time, the average rate of these pulses remains roughly constant, but their exact timing from one pulse to the next is irregular. The same pattern appears in experiments with beams of charged particles, such as electrons. An evacuated tube guides electrons from a source toward a screen coated with a material that glows when struck. At high beam currents, the screen shows a bright patch where many electrons land in a short time. When the current is reduced so that fewer electrons are emitted, the glow becomes dimmer and grainier. With the beam weakened enough, individual electrons can be seen as separate specks of light, appearing at random positions and times on the screen. Each speck fades after a short moment, leaving behind a record if the screen is monitored and the events are stored. Over a long run, the dots build up into a pattern that can be compared with expectations from classical models of the apparatus. The important feature is that the pattern grows through single discrete events that never take fractional values. The detector does not register half of an electron or half of a photon. It responds only when a complete quantum of energy or charge is delivered. In practice, the design of detectors makes full use of this discreteness. A particle counter works by arranging materials so that each incoming particle triggers a chain of physical effects. For example, one particle passing through a gas between electrodes can ionize a few molecules, freeing electrons that are then accelerated by an electric field. These electrons strike other molecules, creating more electrons and positive ions in a cascade. This avalanche produces a measurable pulse of current that can be amplified and recorded. Although the internal details of the cascade involve many microscopic events, the final output is a single pulse of fixed shape and size, which the recording system counts as one. If no initiating particle enters the detector, no avalanche occurs, and no pulse is seen. In optical detectors, a similar strategy is used. When a photon of sufficient energy enters a photomultiplier tube or a solid-state sensor, it ejects or excites an electron in the material. The electron is then guided through a series of stages in which it gains energy and causes more electrons to be released. The result is again a pulse that can be measured as a single event. This design means that the output of the detector is inherently digital in character, even if the incoming beam is adjusted continuously. By counting how many pulses occur in a given interval of time, the experimenter obtains a measure of the intensity of the beam. At the same time, the irregular spacing in time between pulses reveals that the underlying process is not smooth, but granular. In many experiments, the spatial distribution of these discrete events is of central interest. A detector may be divided into many small regions, each capable of registering individual hits. A modern camera sensor, for example, consists of an array of tiny light-sensitive elements that produce signals when photons are absorbed. When a faint image is projected on such a sensor, the raw data appear as a collection of isolated events, each tagged with a position in the array and a time. The brightness of the image at each point is then inferred from how many events accumulate in that region over the exposure period. Even in older setups, using photographic plates, the logic is similar. Photographic grains in the emulsion are sensitive to light. A grain that absorbs enough light undergoes a chemical change during development and becomes part of a darkened region. When the plate is exposed to very weak light, the resulting image can be traced back to the discrete activation of individual grains. In this way, the picture of the world inside the laboratory shifts for many phenomena, especially those involving small amounts of energy or matter measurements, do not reveal continuous variations, but instead produce data that are built from countable units. The instruments register zeros and ones off and on, no event, and one event. The role of the experimenter is to keep careful track of how often and where these events occur. Over many repetitions, statistical regularities appear. For a steady beam of particles with fixed energy, the number of detections in equal time intervals fluctuates, but the average over many intervals remains stable. If the beam intensity is doubled, the average count rate roughly doubles as well. Similarly, if a detector with a finely segmented surface is placed in the path of a beam, certain regions record more hits than others, revealing the structure of the beam and the influence of any lenses, slits, or fields it has passed through. The link between source apparatus and detector becomes clearer when conditions are varied systematically. Changing the energy of the particles or the color of the light alters the rate and distribution of events. Introducing filters or magnetic fields modifies which particles reach the detector. Each set of adjustments corresponds to a different set of experimental conditions, and each condition produces its own pattern of counts. The same apparatus configured in the same way and operated under stable environmental conditions gives patterns that repeat within known statistical margins. These patterns, combined with theoretical models, allow scientists to infer properties of the sources and the intervening elements that are not directly visible. It is important that these discrete detections do not contradict the earlier picture of smooth behavior at larger scales. When the counting rate is very high, individual events blur together and the detector output appears continuous. Macroscopic devices whose function depends on the combined effect of enormous numbers of microscopic events still behave in ways well described by classical laws. For example, an ordinary beam of light from a lamp contains so many photons per second that any imaging system deals only with average intensities. A wire carrying a steady electric current conducts vast numbers of electrons whose individual motions are not resolved in everyday measurements. In both cases, the granular nature of the underlying process is hidden. In the quiet environment of a modern laboratory, however, where sources can be weakened and detectors can be made highly sensitive, the discrete side of nature becomes visible and dominant in the data. The experimental picture of light and matter then includes both the continuous patterns that emerge over long times and large scales, and the individual events that build those patterns up one click or one dot at a time. In the quiet environment of the laboratory, the separate clicks and dots that mark single events invite a different kind of description. When a detector records one event, then another, and then another, with irregular gaps in time between them, it is no longer helpful to speak only in terms of smooth curves. Instead, the pattern is captured by counting how many events occur in each interval and by asking how often a given count appears. This is the language of probability. For a steady source and a stable detector, the number of events registered in equal periods of time fluctuates, but the fluctuations follow a regular statistical pattern. If many intervals are examined, some contain fewer events than the average. Some contain more. Yet, the overall distribution of counts settles into a steady shape that can be summarized in a few numbers. These numbers and the laws that relate them describe how likely different outcomes are, even though the precise timing of any individual event cannot be predicted in advance. In familiar situations, probability enters because of incomplete information. A tossed coin lands on one side or the other. The exact outcome depends on details of the toss, such as the starting angle, the spin, the force, and tiny air currents. In principle, if all these factors were known with great precision, and if the laws of motion were applied carefully, the result could be predicted. In practice, these details are not known, so the outcome is treated as uncertain. Saying that there is an equal chance for the coin to land on either side reflects this ignorance. The same reasoning applies to weather forecasts. The state of the atmosphere at any moment is extremely complex. Even with modern sensors and computers, only an approximate picture can be obtained. When a forecast assigns a certain chance of rain for the next day, that number summarizes how often similar atmospheric situations in the past have led to rain. It does not claim that nature itself is undecided, only that the limited information available to the forecaster prevents a definite statement. In models of gases and liquids, probabilities appear for similar reasons. The motion of each molecule is governed by well-defined laws, but the number of molecules is so large that it is not feasible to track them individually. Instead, statistical methods are used. Temperatures, pressures, and flows are described in terms of average properties of many particles. Fluctuations around these averages can be predicted by considering how many microscopic configurations are compatible with the observed macroscopic state. In all these examples, probability is a tool that helps manage incomplete knowledge or practical limitations. The underlying processes are still viewed as deterministic at a deeper level. Something different emerges in experiments that probe light and matter at very small scales with carefully prepared conditions. Consider a source that emits particles or photons in a way that is as uniform and controlled as possible. The apparatus is arranged so that each emitted object is prepared in the same way, travels through the same environment, and is offered the same set of possible outcomes at the detector. The laboratory is shielded, temperatures are stabilized, and vibrations are reduced. Under these conditions, the classical expectation would be that if all relevant details of the initial state and the intervening forces are fixed, each run of the experiment should give the same result. What is found instead is that even when the preparation and arrangement are repeated with great care, individual outcomes still vary. One trial produces a detection in one region of the detector. A second trial, under apparently identical conditions, produces a detection in a different region, and a third produces no detection at all. Over many runs, the frequencies of the different outcomes approach fixed ratios, but no additional refinement of the setup removes the randomness in the single events. The probabilities do not shrink away as the knowledge of the system improves. They remain as a stable feature of the description. In the standard quantum treatment of such experiments, the theory does not attempt to assign definite trajectories or definite outcomes to individual particles before measurement. Instead, it associates with the prepared system a mathematical object that contains within it all the information that can be known about the possible results of measurements. From this object, rules are used to calculate the probability of each outcome that a given measurement can produce. When the measurement is actually carried out, only one outcome is seen. The others, which also had non-zero probabilities, do not appear in that particular run. The link between the theoretical description and the experimental data is therefore statistical. Quantum theory provides a prescription for computing probabilities, and repeated experiments show that the observed frequencies of different outcomes agree closely with these predictions. Importantly, in this framework, the probabilities are not attributed to hidden details of the system that have been overlooked. They are treated as fundamental. Even if complete control of the preparation were possible, the theory would still assign only probabilities, not certainties, to most measurement results. Many of the puzzles and debates that surround quantum physics trace back to this feature. The idea that probability might be an irreducible part of the description of nature is unfamiliar when viewed from the standpoint of classical physics, where it has always been tied to ignorance or approximation. In the quantum case, experiment after experiment indicates that there is no deeper list of definite properties waiting to be uncovered that would restore a purely deterministic picture at the level of individual events. When attempts have been made to imagine such hidden descriptions and to test them experimentally, the results have consistently supported the standard quantum predictions. Within the laboratory, this change in viewpoint is practical as well as conceptual. Once the behavior of a given setup is characterized, it becomes natural to speak of the probabilities for its various outcomes as measurable quantities in their own right. A device can be calibrated not only in terms of energies and lengths, but also in terms of the chances that it will register one result or another when fed a standard input. Careful counting over many trials becomes a way to determine these chances with increasing precision. The randomness in individual events is not seen as an error to be removed, but as raw material from which stable statistical patterns are formed. In some technologies, this intrinsic randomness is even used as a resource. For example, sources that produce fundamentally unpredictable sequences of detection events can serve as generators of random numbers for tasks that require them. In this sense, probability in the quantum domain is not a sign of poor control, but a basic feature that must be incorporated into both theory and practice. As the study of microscopic systems advances, the language of probability becomes a central part of how their behavior is described. Experimental records consist of long lists of outcomes, each one drawn from a set of possibilities, with known or unknown probabilities. Theoretical descriptions provide rules for computing these probabilities for different arrangements of sources, fields, and detectors. The agreement between the predicted and observed distributions is one of the main tests of the theory. At the same time, the refusal of the individual events to become predictable, no matter how carefully the preparations are made, marks a clear departure from the classical picture in which probability is always secondary. The world revealed by these experiments is one in which chance plays a fundamental role in the link between preparation and outcome, even though the overall statistical structure remains sharply defined and reproducible. The appearance of separate clicks and dots in detectors suggests that at small scales, energy and matter come in discrete amounts. This idea becomes particularly clear in the study of atoms. When gases are heated in discharge tubes or exposed to intense light, they glow with characteristic colors. Passing this light through a prism or a diffraction grating produces not a continuous band of colors, but a pattern of sharp lines at specific positions. Each line corresponds to light of a particular color, which means light of a particular energy. Different elements produce different sets of lines, and these patterns are reproducible with great precision. Classical theories of vibrating charges and continuous radiation have difficulty explaining why only certain energies appear, and why the spectrum consists of isolated lines rather than a smooth spread. The regularity of these spectral lines hints that atoms have internal structures with allowed energy values. Further evidence for discrete energies comes from the stability of matter. In a simple classical picture, an atom consists of a small positively charged nucleus surrounded by negatively charged electrons. The electric attraction between the nucleus and an electron pulls the electron inward, while the motion of the electron tends to carry it past the nucleus. In classical electromagnetic theory, any charged particle that moves in a curved path should radiate energy in the form of electromagnetic waves. As the electron radiates, it loses energy, its orbit shrinks, and it eventually falls into the nucleus. According to this reasoning, atoms with orbiting electrons should be unstable. However, ordinary matter does not collapse in this way. Atoms in solids, liquids, and gases remain intact over very long times. Their chemical properties are well defined and persistent. This conflict between the predictions of naive classical models and the observed stability of atoms indicates that a different kind of description is needed. Quantum theory addresses this by introducing the concept of quantized energy levels. In this view, the electron bound to a nucleus cannot have just any energy it likes. Instead, it is restricted to certain allowed values, which are often called energy levels or stationary states. When the electron is in one of these levels, the atom is stable in the sense that it does not radiate energy continuously. The energy of the bound system changes only when the electron moves from one allowed level to another. These changes do not happen in a smooth, gradual fashion. Rather, they occur as sudden transitions between levels. When an electron in a higher energy level moves to a lower one, the atom emits light. The energy of the emitted photon is equal to the difference between the energies of the two levels involved. Because the levels have definite values, the differences between them have definite values as well. So the emitted photons have discrete energies. This shows up in the spectral lines observed when the light is spread out. Each line corresponds to a transition between a particular pair of energy levels. The regular patterns in atomic spectra, which puzzled researchers in the classical framework, find a natural explanation in this quantized structure. Conversely, when light or other external energy is supplied to an atom, the electron can absorb a photon and move from a lower level to a higher one, provided that the photon energy matches the energy difference between those levels. If the energy does not match, the photon is not absorbed and passes by. In this way, the atom acts as a selective absorber and emitter. Gases absorb and emit light at exactly those energies that correspond to the separations between their internal energy levels. This selectivity underlies many observed phenomena, such as the absorption lines seen in the light from stars, and the emission lines seen in laboratory discharges. Simple atoms like hydrogen provide especially clear cases. The spectrum of hydrogen consists of a series of lines whose positions can be described by a simple mathematical formula. Quantum models that assign specific energy levels to the electron in hydrogen reproduce these line positions with high accuracy. More complex atoms have more complicated spectra, but they also show line patterns that reflect structured sets of allowed energies. As experimental techniques improve finer details, such as small splittings and shifts in line positions are observed, and these too can be traced to features of the quantized energy levels and the interactions between electrons, nuclei, and fields. The quantization of energy levels is not limited to atoms. Electrons confined in solids, molecules, or other structures also exhibit discrete allowed energies. In a solid crystal, for example, electrons move in the periodic environment created by the arranged nuclei. Their allowed energies form bands with gaps where no stable energy states exist. The presence of these bands and gaps explains why some materials conduct electricity easily, some conduct poorly, and some behave as semiconductors. In each case, the underlying description relies on the idea that electrons cannot occupy arbitrary energies, but must reside in states determined by the structure of the system. In small systems, such as atoms and molecules, the spacing between adjacent energy levels can be quite large on microscopic scales. This means that only certain photon energies can be emitted or absorbed in transitions. In larger or more complex systems, the levels can lie closer together and bands of nearly continuous energies can appear. But the basic principle remains: there are underlying discrete states whose arrangement guides the observable behavior. The presence of quantized energy levels is closely linked to the wave-like character of bound systems. When an electron is confined by the attractive force of a nucleus, the allowed states correspond to wave patterns that fit within the region in a stable way, much as only certain standing wave patterns fit on a string fixed at both ends. However, in the quantum case, the wave description applies not to a material disturbance in space, but to a mathematical function used to calculate probabilities. This function must satisfy certain conditions, and only particular energy values allow those conditions to be met. The result is a spectrum of allowed energies with no states in between. Although the full mathematical treatment can be intricate, the broad physical picture is clear. Confinement and wave-like behavior together force the existence of discrete states. The combination of quantized energy levels and discrete detection events leads to a coherent view in which the microscopic world is organized in steps rather than in a fully continuous way. Atoms remain stable because electrons in allowed states do not radiate energy steadily. And when energy is exchanged between matter and radiation, it does so in well-defined amounts. A photon emitted in a transition carries away a specific energy, and a photon absorbed in a transition must supply a matching energy. Photons themselves are associated with discrete packets of electromagnetic energy. So the interaction between light and matter is framed in terms of exchanges between quantized entities. These ideas feed directly into practical technologies. The operation of lasers depends on creating a population of atoms or other systems in excited energy levels and encouraging them to emit photons in a coordinated way as they move down to lower levels. The output of a laser is a beam of light with a very narrow range of energies corresponding to one or a few specific transitions. In semiconductors, the band structure of allowed energies in the material determines how electrons move when a voltage is applied and how they respond to incoming light. Devices such as light-emitting diodes and photovoltaic cells rely on electron transitions between bands and on the quantized nature of these transitions. Even though these technologies operate in macroscopic devices, their behavior is governed by the underlying discrete energy structure at the microscopic level. The concept of quantized energy levels therefore plays a central role in connecting the granular data from detectors to the stability and properties of matter. Spectral line stable atoms and the operation of modern electronic and optical devices all point to a world in which certain physical quantities do not vary continuously, but instead take on specific allowed values. Within this framework, the familiar regularities of everyday materials and the precise patterns seen in sensitive experiments can be understood as consequences of the same underlying structure. Among the many properties that microscopic particles possess, one of the simplest and most useful in quantum physics is called spin. In everyday language, spin suggests a small object turning around on its axis, but in the quantum description, it is better thought of as an internal property that shows itself in specific measurement outcomes, not as a tiny ball literally spinning in space. The important feature is that for particles, such as electrons, a measurement of spin along a chosen direction can give only one of two possible results. These results are often called spin up and spin down along that direction. There are no intermediate values in between, no continuous range of orientations produced by the same measurement. This two-valued character makes spin a clear example of how quantization appears not only in energy levels, but also in other basic properties. A classic way to reveal this is to send a beam of atoms with a single unpaired electron, such as silver atoms, through a region where there is a magnetic field that changes with position. The apparatus is arranged so that the atoms travel in a narrow beam, pass between specially shaped magnet poles, and then strike a detector screen. If the internal magnetic moments associated with the electrons were oriented at random with all possible angles, classical reasoning would suggest that the forces in the field would spread the beam into a continuous band on the screen. Instead, when the experiment is carried out carefully, the beam splits into two distinct parts. One group of atoms is deflected in one direction and forms a spot at one position, and the other group is deflected in the opposite direction and forms a second spot at another position. There is no broad smear between these spots. This pattern indicates that with respect to the chosen direction in space, each atom in the beam is in one of two spin states that produce different forces in the magnetic field. Repeating the experiment with the same arrangement gives the same two-spot pattern, and the relative numbers of atoms in each spot remain stable within statistical limits. If the beam is first passed through such a magnet and only one of the two emerging beams is allowed to continue, then all the atoms in that selected beam have the same spin result with respect to that direction. When this purified beam is sent into a second magnet aligned in the same way, all the atoms go to the same spot again. The outcome is now predictable because the preparation has fixed the spin result along that axis. The situation becomes more subtle when the second magnet is turned to a different orientation. If the spin of each atom were a simple classical arrow pointing somewhere in space, and if the first magnet had forced all these arrows to point, for example, up along its own direction, then a second magnet tilted by some angle might be expected to deflect the beam into a single spot shifted accordingly. What is observed instead is that the second magnet again splits the beam into two spots, corresponding to spin up and spin down along its new direction with certain probabilities for each outcome. No further refinement of the apparatus removes this two-valued result. Once a direction of measurement is chosen, the spin measurement yields only one of two possible values. The theory that describes this behavior treats spin as a quantity that is inherently quantum in character. It is not just that practical limitations prevent us from seeing a continuum of orientations. Rather, the allowed outcomes for a given measurement direction are discrete. Before the measurement is made, the state of the particle encodes in a precise mathematical way the probabilities for the two possible results. When the measurement is performed, exactly one of these results is obtained. If the same measurement is repeated immediately on the same particle in the same conditions, the same result is obtained again with certainty. Yet, if a different measurement along a different axis is made, instead, the outcomes are again split into two possibilities with new probabilities. In this picture, there is no single list of definite spin values for all directions that exists independently of the measurements that are actually carried out. The simplicity of spin makes it a natural building block for quantum information. A system that has two distinguishable states available to it can be used to represent a single unit of information. In classical systems, this unit is called a bit and takes the value 0 or 1. In the quantum setting, an idealized two-state system, such as the spin of an electron along a chosen axis, plays an analogous role and is called a quantum bit or qubit. At first glance, a qubit seems to be just a more delicate version of a classical switch which can be either in one position or the other. However, the quantum description allows a more general kind of state for the qubit encoded in the way probabilities are assigned to the two outcomes of any chosen spin measurement. For a given measurement direction, there can be a state in which one outcome has probability 1 and the other has probability 0, similar to a definite classical setting. There can also be states in which both outcomes have non-zero probabilities, such as equal chance for up or down, or some fixed unequal ratio. These probabilities are not treated as expressing ignorance about a more detailed underlying configuration. They are part of the fundamental description determined by how the qubit has been prepared. When a measurement is carried out, one result occurs according to these probabilities, and the state of the qubit is updated to reflect the new situation. The rules governing how the probabilities depend on the choice of measurement direction and on previous preparation are specific and testable. They differ from what would be expected if spin were an ordinary vector, whose components along different axes were all predetermined. Experiments with beams of atoms and with individual spins in solid materials have confirmed these quantum rules in many variations. The ability to control spin states has practical consequences. In magnetic resonance techniques, for example, spins in a material are influenced by carefully tuned magnetic fields and oscillating radio frequency fields. By adjusting the strength, frequency, and timing of these fields, experimenters can change the spin states in controlled ways and then detect their response. The signals obtained carry information about the local environment of the spins and about the structure of the material. In these applications, spin behaves as a quiet but reliable probe of microscopic conditions. In systems designed to act as qubits for quantum computing, spin states are isolated as much as possible from random disturbances so that they retain their well-defined quantum character for longer times. Operations on such qubits are implemented by sequences of controlled interactions that rotate their spin states in a structured way. The details of these operations and the way they combine rest on the same basic quantum description of spin that was first revealed by the splitting of atomic beams in magnetic fields. At a conceptual level, spin shows how a quantum property can be both quantized and probabilistic at once. The possible outcomes of a spin measurement along a chosen direction form a simple two-valued set with no intermediate results. Yet, unless the system has been prepared in a special way that makes one of these outcomes certain, the theory assigns probabilities to them rather than definite predictions for each single trial. The observed frequencies of spin up and spin down in repeated experiments match these probabilities, and no deeper pattern has been found that would reduce them to hidden classical variables. In this way, spin provides a compact and concrete example of the broader features of quantum physics that have already appeared in discussions of discrete events and quantized energies. It introduces a property that cannot be fully understood using only classical images of small objects moving and rotating in space, but which can nevertheless be measured, manipulated, and used with great precision in the laboratory. In the quantum description of microscopic systems, the discrete outcomes seen in measurements such as spin up and spin down are only part of the story. Between the preparation of a system and the act of measuring it, the theory does not describe the system as already holding one of these outcomes in a hidden way. Instead, it assigns to the system a state that can be thought of as containing several possible outcomes at once, each with an associated weight. This situation is called superposition. It does not mean that a particle is literally in two places in space at the same time in a simple everyday sense, or that a spin is physically pointing both up and down at once. Rather, it means that the most complete description available before measurement involves a combination of contributions from states that would, if measured, give different results. These contributions do not simply represent ignorance, as classical probabilities do. They form a structured object from which both probabilities and other features, such as the way systems combine and interfere, can be calculated. For a simple two-state system, like the spin of an electron along a chosen direction, there are two basic states that give definite outcomes, if measured: one that always yields spin up and one that always yields spin down for that direction. In the quantum framework, a general state of this spin is built from these two basic states. If the spin is prepared so that a measurement along that direction always gives spin up, then the state coincides with the spin-up state. If it is prepared so that a measurement always gives spin down, its state coincides with the spin-down state. But many preparations do not lead to certainty. They lead instead to outcomes in which spin-up occurs with some fixed probability between 0 and 1, and spin-down occurs with the complementary probability. The corresponding quantum state is then a superposition of the basic up and down states with weights that are related to these probabilities. The key point is that this superposition encodes more than just the bare numerical chances for the two results. It also carries information about relative phases, a kind of internal angle that affects how the state behaves if a different measurement is performed or if the system is combined with others. Different superpositions that have the same probabilities for one measurement can give different statistics for another measurement. This is one way in which the quantum state goes beyond a simple list of outcome frequencies. Before the measurement, the spin in such a superposition does not have a definite value along the chosen direction, in the same sense that a classical arrow does. The quantum state assigns only probabilities to each possible result. When the measurement finally takes place, one of the two outcomes is registered. The detector records a single click in one channel or the other, never both at once. After this point, if the same measurement is immediately repeated, the result is found to be the same with very high reliability. In the standard quantum rules, this behavior is captured by saying that the measurement process changes the state of the system. A state that was previously a superposition of up and down with both outcomes possible is transformed into a state that corresponds to the outcome actually obtained. If the result is spin up, the state becomes the pure up state. If the result is spin down, the state becomes the pure down state. Subsequent measurements of the same type then yield that result with certainty, at least until some new interaction or evolution changes the state again. This updating of the state is sometimes called collapse, but it is best regarded here simply as a rule for connecting the mathematical description to the observed facts that measurements produce definite outcomes. Superposition appears not only in spin, but in many other contexts. An electron bound in an atom can be prepared in a state that is not a simple energy level, but a combination of two or more allowed energy levels. In such a case, careful measurements of the energy do not always give the same value. Instead, one of the contributing energy values is found in each trial, with probabilities determined by the structure of the superposition. Over time, the relative phase between the energy components can change in a predictable way, leading to observable effects, such as oscillations in the probabilities of certain outcomes. Again, the superposed state is not a sign that the system is secretly in one energy level or another, and that the experimental simply does not know which. It is a genuine combination in the quantum sense, which can produce interference effects when different parts of the state are allowed to evolve and then are brought together in a measurement. This sensitivity to relative phase distinguishes quantum superpositions from ordinary statistical mixtures. In a classical mixture, a preparation might involve, for example, half of the systems having one property and half having another with no further structure. The probabilities for outcomes in any test simply reflect these proportions. In a quantum superposition, even when the probabilities for one test match those of a classical mixture, the underlying state can still behave differently in other tests because of the way its components combine. Experiments have been designed in many settings to reveal this difference, and they consistently show that superposition is a real feature of microscopic systems, not just a mathematical device. The role of measurement in this picture is delicate but precise. Between measurements, the state of an isolated system is taken to evolve according to a fixed rule that is deterministic and reversible. Given the state at one time, the state at a later time is fully determined, and in principle, the earlier state can be recovered from the later one by reversing the evolution. This continuous law-governed change preserves the detailed structure of superpositions, including their relative phases. When a measurement is carried out, however, the link between state and outcome involves probabilities. The theory provides a rule for calculating the probability of each possible outcome from the current state. Once an outcome is obtained, the state is updated to match that outcome for future predictions. This two-part rule with smooth evolution between measurements and probabilistic changes at the moments when measurements occur is one of the distinctive features of quantum theory. It reflects the experimental fact that while the overall patterns of outcomes can be predicted very accurately from the way systems are prepared and allowed to evolve, the individual results of many kinds of measurements remain inherently uncertain. Superposition makes this uncertainty structured rather than random. It tells for any given preparation how the uncertainty is distributed among the possible outcomes, and how those distributions change when different questions are asked of the system. In the controlled conditions of a laboratory, this structure can be tested and used. Devices that manipulate spin states or energy levels exploit superposition to achieve specific transformations, such as rotating a spin from one direction to another or creating a balanced combination of states that gives equal probabilities for different results. Quantum bits in information processing are deliberately prepared in superpositions to make use of their ability to encode more than a simple 0 or 1 along a single measurement direction. In these applications, superposition is treated not as a philosophical curiosity, but as a working resource. From the broader perspective of this discussion, the concept of superposition marks a further step inward from the discrete clicks of detectors and the quantized energies of bound systems. It introduces a level at which the basic categories of outcome, such as spin up and spin down, are combined in ways that have no direct analog in classical physics, yet lead to sharply defined and testable predictions. Measurements still produce definite results in single trials, but the states that lead to those results are described by combinations of possibilities, whose interplay emerges only through repeated experiments and careful analysis of statistical patterns. As the quantum description of microscopic systems develops, it becomes clear that there are limits on how sharply certain pairs of physical quantities can be defined for the same system at the same time. These limits are not merely practical, arising from imperfections in instruments or disturbances caused by clumsy measurements. They are built into the structure of the theory itself and are confirmed by experiments that approach the limits of what can be done in controlled conditions. This set of ideas is often gathered under the term uncertainty, but it is important to understand that the word here refers to a basic feature of how quantum states are defined, rather than simply to the experimenter's lack of knowledge. A familiar example involves position and momentum. Position describes where a particle is in space, while momentum, which for a given mass is closely related to velocity, describes how fast and in what direction it is moving. In classical physics, both quantities are assumed to have definite values at every instant. A point mass moving along a line has a precise location on that line and a precise speed, even if those values are not known in practice. In quantum theory, the state of a particle is associated with a mathematical object that can be used to calculate probabilities for different outcomes of position or momentum measurements. When the state is such that the position is very well localized, meaning that a measurement of position is very likely to yield a result within a small region, the same state necessarily corresponds to a wide spread of possible momentum values. When the state is arranged so that momentum is sharply defined with a narrow range of likely values, the corresponding position distribution becomes broad. No state allows both position and momentum to be concentrated into arbitrarily narrow ranges at once. The product of the spreads has a lower bound that cannot be crossed by any preparation. This is what is meant by an uncertainty relation. One way to see the origin of this relation is to recall that quantum states have wave-like aspects. A state that is sharply localized in position corresponds in the wave description to a pattern that is formed from a wide range of underlying wave components. Each component is associated with a particular momentum value. Combining many components with different momenta makes it possible to construct a state that is confined to a small region in space, but the price paid is that the momentum content becomes spread out. Conversely, a state that corresponds to a single underlying wave component with a well-defined momentum extends broadly in space. It cannot be used to represent a particle that is known to be confined to a narrow region. This trade-off is not a matter of technical difficulty in building the waves. It follows from the basic rules for how these wave descriptions are connected to position and momentum. In the laboratory, uncertainty relations show up when attempts are made to prepare and measure states that would, in classical thinking, combine precise knowledge of both position and motion. For example, one might try to confine a particle tightly in a trap to localize its position and then measure its momentum accurately. The act of confinement itself, which ensures that the particle is likely to be found within a small region, requires conditions that unavoidably introduce a spread in momentum. When a measurement of momentum is performed on such a state, The results are scattered over a wider range than would be expected from a classical picture of a particle sitting almost at rest in a small box. Efforts to design measurements that disturb the particle as little as possible still confront the same pattern. No sequence of gentle probes can produce data that assign sharply defined values to both quantities at once. Similar relations hold for other pairs of quantities, such as different components of spin or different combinations of position and energy. In each case, the quantum state can be prepared in ways that make one quantity very sharp at the expense of making the other more uncertain, or that balance the uncertainties between them, but there is always a lower bound to how small the combined uncertainty can be. These bounds are expressed mathematically in compact formulas, but their physical content is captured by the idea that certain questions about a system cannot simultaneously be answered with arbitrary precision. The limitation is not due to a lack of effort or to crude methods. It is a structural feature of the theory that has been confirmed many times by experiments using refined apparatus. It is tempting to imagine that the uncertainty arises because any measurement necessarily disturbs the system. For instance, to see a very small object under a microscope, one may shine light on it. The light must have a short wavelength to resolve fine details, which in turn implies that each photon carries higher momentum. When such a photon scatters from the object, it changes the object's motion in a noticeable way. This picture can be helpful in illustrating that measurement can influence what is being measured, but it does not capture the full content of quantum uncertainty. Even if one considers idealized measurements that minimize disturbance, and even if one thinks of the state before any measurement is made, the uncertainty relations still apply. They concern what it is possible to encode in a single quantum state, not just what can be extracted without perturbation. When many identically prepared systems are measured, the spread of results for position and momentum reflects these limits. The uncertainty relations therefore guide both theoretical expectations and experimental design. They indicate which combinations of quantities can in principle be made sharp together and which cannot. This influences how experiments are set up and how the results are interpreted. For example, in atomic physics, it is understood that trying to confine an electron too tightly will give it a large spread in momentum, which can result in higher kinetic energy and can affect the stability of the system. In precision measurements trade-offs between time resolution and energy resolution, or between different components of a field, are considered in light of the relevant uncertainty relations. Rather than being seen as a nuisance or a failure, these limits are treated as part of the landscape within which quantum phenomena occur. At the same time, it is important to note that uncertainty does not mean vagueness in all respects. Quantum states can be prepared so that some quantities are known with great precision, and predictions about those quantities can be extremely accurate. The spreading is confined to particular pairs or combinations. The theory provides clear rules for calculating both the sharp values and the spreads. Careful experiments using beams of atoms, trapped ions, photons in cavities, and other systems have verified these rules in detail. In such experiments, as the preparation of states is adjusted to make one variable more precise, the observed spread in the conjugate variable increases in exactly the way predicted by the uncertainty relations. In this way, the quantum notion of uncertainty defines what can and cannot be simultaneously known about a system in a single state. It does not say that nothing definite can ever be said. Instead, it draws a boundary around the combinations of precision that are allowed. Inside that boundary, the theory and experiments align closely. Outside, it classical expectations that all quantities can be sharply assigned at once do not hold. This shift in perspective marks another step inward from the classical picture of particles with well-defined positions and speeds. It provides a framework in which the wave-like aspects of quantum states and the discrete outcomes of measurements are connected by structured limitations on knowledge that are themselves stable, quantitative, and reproducible. In many branches of physics, waves provide a useful way to describe how disturbance is spread in space and time. On the surface of water, a small splash creates ripples that move outward, rise and fall, and eventually fade. In air, sound travels as a pattern of slight compressions and rarefactions that move from a source to a listener. In both cases, the waves can be pictured as extended patterns in which many points move in a coordinated way. When two sets of waves overlap in the same region, the total effect at each point is determined by adding their contributions. Where the crests of one wave align with the crests of another, they reinforce and produce a larger disturbance. Where the crest of one wave aligns with the trough of another, they cancel and produce a smaller disturbance or none at all. This combining of contributions, sometimes called interference, is a general feature of wave phenomena. Light also behaves as a wave in many situations. When a beam of light passes through a narrow opening or around an obstacle, it spreads out rather than continuing in a perfectly straight line. When two or more beams meet, they can form regions of greater brightness and regions of darkness, arranged in patterns that depend on how the waves line up. Experiments with thin films gratings and multiple slits show these interference patterns in great detail. Classical wave theory accounts for them by treating light as an electromagnetic wave with a certain amplitude and phase at each point. The amplitude describes the strength of the wave, while the phase describes the stage of the oscillation, somewhat like the position of a hand on a clock face. When two waves meet, their amplitudes are added, taking into account both size and phase. The resulting pattern of reinforcement and cancellation explains the observed bright and dark regions. In quantum physics, the wave idea appears in a new role. Instead of describing a material medium or a classical field, the wave-like object associated with a particle is used to calculate probabilities for different measurement outcomes. For a single particle moving through space, the quantum state can be represented by a function that assigns to each point a quantity similar in some ways to a classical wave amplitude. This quantity has both a size and a phase. The size, when used in a specific way, determines the probability of finding the particle near that point if a position measurement is made. The phase does not appear directly in the probability, but it plays a crucial role when different parts of the state are allowed to combine. In regions where contributions with different phases overlap, they can interfere in much the same way that classical waves do. Some combinations enhance the probability of detection, while others reduce it. The rules are precise. The quantum amplitudes associated with different possible paths or configurations are added, and the resulting total is then used to compute probabilities. A simple illustration involves a particle that can reach a detector by following two alternative routes. In a classical picture, if the particle is like a small solid object, one would expect it to choose one route or the other, in each run with some probability for each route. The total probability of arrival at the detector would then be obtained by adding the probabilities for the two routes. There would be no possibility of cancellation because probabilities are always non-negative and simply accumulate. In the quantum description, each route is assigned an amplitude which has both size and phase. The total amplitude at the detector is obtained by adding the amplitudes for all routes. Because of the phases, the contributions can add or cancel before the probability is computed. In some directions or at some positions on the detector, the amplitudes reinforce, leading to a higher probability of detection than either route alone would give. In other directions or positions, the amplitudes cancel, leading to a much lower probability, possibly close to zero, even though each route on its own would allow the particle to arrive there. This interference of amplitudes underlies the pattern seen in many quantum experiments. The connection between amplitudes and probabilities adds structure to the concept of superposition. When a quantum state is written as a combination of contributions from different configurations, each contribution carries an amplitude. The relative sizes and phases of these amplitudes determine not only the probabilities for different measurement outcomes, but also how these probabilities change when the system is subjected to different arrangements of apparatus. For example, in an experiment with several slits or paths closing, one path does more than simply removing one term from a list of classical alternatives. It changes the pattern of interference between amplitudes and therefore changes the entire distribution of detection probabilities on a screen. The effect can be counterintuitive if one thinks only in terms of particles choosing definite routes, but it becomes natural when viewed in terms of waves that combine. Yet it is important to remember that in quantum physics, what interferes are not classical waves of material displacement, but probability amplitudes. This wave-like description does not contradict the discrete outcomes seen in detectors. In fact, it provides a way to understand how those outcomes are distributed. When a particle is sent repeatedly through a fixed arrangement and the positions of its detections are recorded, the individual dots build up a pattern over time. In regions where the squared size of the total amplitude is large, many detections accumulate. In regions where this quantity is small, few or no detections occur. The interference of amplitudes thus shapes the pattern even though each run of the experiment results in a single detection at a single location. The smooth variation of the underlying amplitude and the granular nature of the detection events coexist in a consistent way. When the intensity of a source is increased so that many particles are present at once, the interference pattern emerges more quickly, but its shape remains the same. Classical waves and quantum amplitudes share some mathematical features, but their physical interpretations differ. In a water wave, the amplitude at a point corresponds directly to the height of the water surface, which can, in principle, be observed at any moment. In a quantum state, the amplitude is not something that can be measured directly in a single run. It is a tool for computing the probabilities of the outcomes of different possible measurements. Changing the arrangement of the apparatus, such as inserting or removing barriers, lenses, or fields, alters the way amplitudes propagate and combine, and thereby alters the observable probabilities. Because of this, descriptions that rely only on trajectories of particles are often insufficient to account for the details of experimental results. The wave-like aspect encapsulated in the amplitude formalism is needed to capture how different possibilities support or suppress each other. The idea that a particle is associated with a spread-out amplitude that can interfere with itself becomes especially significant when experiments are designed to reveal this behavior directly. Arrangements in which only one particle is present in the apparatus at a time still produce interference patterns in their accumulated detection records, indicating that the amplitude associated with a single quantum object explores multiple routes. When parts of the apparatus are modified so that information about the path becomes available in principle, the interference pattern changes or disappears, reflecting the altered structure of the underlying amplitudes. These observations reinforce the view that the wave description in quantum physics is not an optional picture layered on top of a more basic particle story. It is an essential part of how probabilities are determined. From a broader viewpoint, the introduction of amplitudes and interference adds another layer to the inner structure of the quantum world. Starting from discrete detection events and quantized energies, the theory progresses to superpositions and uncertainty relations, and then to a full wave-like description in which the key quantities are complex amplitudes whose interference shapes the probabilities of outcomes. This framework is used not only for single particles, but also for many body systems and fields where it becomes more intricate, but retains the same core principles. Within this approach, familiar wave phenomena and novel quantum effects are described in a unified way, preparing the ground for deeper topics such as the behavior of entangled systems and the correlations they exhibit across space. A particular arrangement in the laboratory brings together many of the quantum features already discussed into a single experiment. The setup consists of a source that emits particles, a barrier with two narrow openings, and a detection screen some distance beyond the barrier. The particles can be electrons, photons, or other microscopic objects that can be produced one after another in a well-controlled way. The barrier is made so that the openings or slits are narrow, compared with the distance between the barrier and the screen, but wide enough that particles can pass through. The screen is sensitive enough to register the arrival of individual particles as small marks or flashes. When the apparatus is aligned and shielded so that stray influences are minimized, the pattern of marks on the screen reveals how the particles travel from the source to the detector under these conditions. In a classical particle picture, where each particle is imagined as a small localized object following a definite path, the expected outcome seems straightforward. Each particle leaves the source, travels toward the barrier, and passes through either the left slit or the right slit. After passing through it, continues on and eventually reaches the screen, where it lands at some position. If many particles are emitted in this way, and both slits are open, the screen should show two overlapping patches of impacts. One patch corresponds to particles that pass through the left slit, and the other corresponds to particles that pass through the right slit. The detailed shapes of these patches depend on the geometry and on any small random deviations in the trajectories. But the overall pattern is expected to be smooth, with more particles arriving in regions directly in line with the slits, and fewer arriving far to the sides. If one slit is closed, and only the left slit remains open, then the screen should show a single patch of impacts corresponding to the paths through that slit. Likewise, if only the right slit is open, the screen should show a single patch corresponding to the right slit. When both slits are open, the classical expectation is that the pattern would simply be the sum of these two single slit patterns, where either slit alone would give many impacts, the combined pattern would show more. Where either would give few, the combined pattern would show few, and there would be no strong modulation beyond the overlap of the two smooth profiles. Wave behavior gives a different prediction. If a continuous wave, such as a water wave or a classical electromagnetic wave, is sent toward a barrier with two slits, each slit acts as a source of a new wave that spreads out beyond the barrier. At the screen, the contributions from the two waves combine. In some regions, the crests of the waves from the two slits arrive together and reinforce, producing large disturbances. In other regions, a crest from one slit arrives together with a trough from the other, and they cancel, leaving little or no disturbance. The result on the screen is an interference pattern, a series of bright and dark regions where the combined wave has respectively high and low intensity. If the intensity is recorded, it shows alternating bands, rather than two simple overlapping patches. When actual double-slit experiments are performed with particles in the quantum regime, the observed pattern on the screen matches the wave prediction, rather than the classical particle prediction. With both slits open and the source adjusted so that many particles arrive in a short time, the distribution of impacts on the screen shows a series of bright and dark bands with clear regions, where relatively few particles land, even though each slit by itself would allow particles to arrive there. The positions of the bright bands correspond to places where the wave contributions from the two slits reinforce, and the dark or dim regions correspond to places where they cancel. This is already surprising from a naive particle viewpoint because it suggests that somehow the presence of both slits affects where particles land, even though each particle is detected as a single localized event. The surprise deepens when the experiment is modified so that only one particle is present in the apparatus at any time. The source is adjusted to emit particles so rarely that the chance of two particles being in flight at once is negligible. The detector is sensitive enough to register each arrival separately. Under these conditions, the screen initially shows isolated dots, each marking the landing position of one particle. The dots appear at apparently random locations with no immediate sign of a pattern. However, as more and more particles are sent through and their positions are recorded, a familiar shape emerges. The density of dots in different regions of the screen builds up into the same interference pattern that was seen when many particles were present at once. Bright bands correspond to regions where over time many detections occur, and dark bands correspond to regions with few or no detections. This behavior indicates that the wave-like interference cannot be explained by interactions between different particles, because it occurs even when the particles arrive one after another. Instead, it points to the conclusion that the quantum description for a single particle must involve something that behaves like a wave, spreading through both slits and interfering with itself. In the language of amplitudes, each possible path that a particle can take from the source to a point on the screen is assigned a quantum amplitude, which has both size and phase. For a given point on the screen, contributions from all such paths must be taken into account. When both slits are open, there are many paths that go through the left slit and many that go through the right slit, and their amplitudes combine. At points where the amplitudes from the two families of paths align in phase, they add and give a larger total amplitude, leading to a higher probability of detection. At points where they are out of phase, they partially or completely cancel, leading to a low probability. The probability of detecting a particle at a given point is determined by the squared size of the total amplitude there. Over many trials, the pattern of detection frequencies reflects this underlying structure. When one slit is closed, the paths through that slit are removed, so their amplitudes do not contribute. The remaining amplitudes from the open slit do not form the same interference pattern as before, because there is no second family of contributions with which to interfere. The distribution of detection probabilities on the screen changes to a smooth pattern similar to what would be expected from a single source. This change illustrates that one cannot think of the two slits simply as independent routes that particles sometimes take. The pattern with both slits open is not just the sum of the patterns with each slit opened separately. Instead, the combined pattern arises from the way amplitudes from both routes interact. Another variant of the experiment explores the role of information about which slit the particle passes through. It is possible, in principle, to place additional devices near the slits that interact with the particles and leave a mark that can later be used to infer which slit was taken. For example, one could imagine a detector that responds differently when a particle passes through the left slit than when it passes through the right slit. When such which path information is available, even if it is not actually read out in a particular run, the interference pattern on the main screen is altered. The clear bands fade, and the distribution of detection events approaches the pattern predicted for a simple mixture of particles going through one slit or the other without interference. This behavior reflects the fact that the quantum state has changed. The correlation between the particle and the path-marking device modifies the structure of the amplitudes so that the contributions that would have interfered are now associated with distinguishable outcomes, and the interference is reduced or lost. When the which path information is removed or made inaccessible before detection at the screen, the interference pattern can reappear. These variations show that the presence or absence of interference depends not only on the physical openings in the barrier, but also on the overall arrangement that determines which alternatives are effectively combined in the quantum state. The double-slit experiment therefore condenses many central aspects of quantum physics into a single arrangement. Discrete detection events show that the detector responds in individual units. The buildup of a stable pattern over many events shows that probabilities, not certainties, govern single outcomes, but that these probabilities are reproducible and well-defined. The form of the pattern with alternating bright and dark regions that disappear when one slit is closed, or when which path information is introduced, shows that a wave-like amplitude associated with each particle explores multiple routes, and that the interference of these amplitudes shapes the distribution of outcomes. The experiment also illustrates the role of measurement arrangements in defining which questions are being asked of the system and which aspects of the quantum state are revealed. All of these features appear without invoking complex systems or advanced mathematics. They arise simply from careful control of sources, barriers, and detectors, and from meticulous counting of detection events on a screen. In this way, the double-slit experiment serves as a clear bridge between the earlier discussion of discrete events, quantized properties, superposition, uncertainty, and wave interference, and the more complex behaviors that appear when multiple quantum systems interact and share correlations across space. When more than one quantum system is considered at the same time, new features appear that cannot be captured by simply assigning independent states to each part. The most striking of these features is called entanglement. It arises when the joint state of two or more systems cannot be written as a simple combination of states for each part separately. Instead, the complete description links the parts in a way that shows up in the correlations between measurement outcomes, even when the systems are far apart. Entanglement is not a rare or exotic occurrence. It appears naturally whenever quantum systems interact and then separate without losing the connections established during their interaction. To see how entanglement emerges in a concrete way, it is helpful to return to the example of spin. Consider two particles each, with a spin that can be measured along some chosen axis, giving outcomes that are labeled up or down. If the two particles are prepared independently, it is possible to describe the combined system by saying that the first particle has its own spin state, and the second has its own with no special relation between them. Measurements on the first then have no effect on the statistics of measurements on the second, and vice versa, except through ordinary classical correlations that might have been introduced by the way the preparation was chosen. However, when the two particles interact, for example, during a process in which they are created together from a common source, the situation can be different. The joint quantum state can be such that certain combinations of measurement outcomes are strongly favored, while others are suppressed in ways that cannot be obtained by any assignment of independent properties to each particle alone. In this case, the system is said to be entangled. A simple example of an entangled state is one in which the total spin of the pair is zero. For two spin 1/2 particles, this can be arranged so that whenever a measurement of spin along any chosen axis is performed on both particles, the results are always opposite. If one particle is found to be spin up along that axis, the other is always found to be spin down along the same axis. If the measurement axis is changed to a different direction, and both spins are measured again on fresh pairs prepared in the same way, the same anti-correlation appears. No matter how the axis is chosen, the outcomes are always opposite. The quantum state that produces this behavior is entangled. It cannot be described by saying that each particle carries its own independent spin value that is simply revealed by measurement. Instead, only the joint properties are sharply defined. The structure of this state becomes apparent when the particles are allowed to move apart after preparation. They can be sent in opposite directions, so that after some time they are separated by a large distance. If measurements of spin along the same direction are then made on each particle, the anti-correlation persists. Each side sees a random sequence of up and down results, with each outcome occurring with equal frequency. But whenever the records from the two sides are compared, it is found that every time one detector registered up, the other registered down, and vice versa. This pattern holds no matter how far apart the detectors are, as long as the particles have not interacted with other systems in a way that destroys the entanglement. The correlations here are stronger and more structured than those that would arise from a simple classical arrangement in which each particle is given a definite spin value at the source and then travels to its detector. In a classical model of that kind, it is possible to assign to each particle a set of instructions determining how it should respond to measurements along different possible axes. If the axes chosen for measurement are fixed in advance, these instructions can be arranged to reproduce the observed anticorrelations. For example, one particle could carry the instruction to be up along a particular axis and down along the opposite, while the other carries the opposite instructions. However, in quantum experiments, the measurement axes can be chosen at the last moment and can differ between the two sides. When entangled pairs are subjected to measurements along varying independently chosen directions, the observed correlations between outcomes violate general constraints called Bell inequalities that would hold for any model based on local hidden instructions of this kind. The quantum predictions for the joint probabilities of outcomes as functions of the relative angles between the measurement axes differ from the predictions of such classical models, and careful experiments have confirmed the quantum predictions. These experiments typically involve sources that emit entangled pairs of photons or other particles, long paths that carry them to separated measurement stations and devices at each station that can rapidly switch the orientation of the spin or polarization measurement. The outcomes are recorded and later compared. By analyzing the statistics of many runs, researchers test whether the patterns satisfy or violate the inequalities derived from local hidden variable assumptions. The results consistently support the quantum description, showing that no model in which each particle carries only its own predetermined set of responses, independent of the distant measurement setting, can account for the observed data. In the quantum framework, the explanation lies in the structure of the entangled state and in the rules for assigning amplitudes and probabilities. The joint state of the pair encodes correlations directly. It specifies that certain combinations of outcomes have high probability and others have low or zero probability. When a measurement is made on one particle, the overall state is updated in a way that takes the outcome into account and adjusts the probabilities for subsequent measurements on the other particle. This updating is not a signal that travels between the particles in space in the usual sense. It is a change in the description used to make predictions based on the new information about the result on one side, and it is required to maintain agreement with the tight statistical constraints that have been observed. Importantly, even though the correlations are strong, they cannot be used to send usable messages faster than light. The measurement outcomes at each side taken alone form random sequences. It is only when the results from both sides are brought together and compared using ordinary communication channels that the correlations become visible. This ensures that the quantum behavior does not contradict the usual limitations on information transfer imposed by relativity, even though it goes beyond classical expectations about how distant systems should behave. Entanglement also appears in many other forms. States can be constructed in which the spins of two particles are correlated rather than anti-correlated, or in which more than two particles share linked properties in more complex patterns. Position and momentum variables, as well as other internal degrees of freedom, can be entangled. In such cases, measuring a quantity on one part of the system immediately constrains the possible results of measurements on the other parts, even if they are distant. The common feature is that the full quantum state encodes joint properties that cannot be decomposed into properties of each component alone. From a practical viewpoint, entanglement has measurable consequences for the distribution of probabilities in experiments. When entangled systems are used, joint measurements can yield outcome distributions that are impossible to obtain from uncorrelated or classically correlated systems. This can be tested by comparing the performance of devices that rely on entanglement with those that do not in tasks such as certain kinds of measurement communication or state preparation. In all these cases, the distinctive feature is the presence of non-classical correlations that reflect the shared quantum state of the parts. From the standpoint developed in earlier sections, entanglement represents another step inward in the structure of quantum theory. Beginning with discrete detection events and quantized properties of single systems, the discussion progressed through superposition, uncertainty, and interference. Entanglement extends these ideas to composite systems, where the combination of states leads to new behavior that cannot be reduced to independent descriptions of each part. The correlations it produces are stable, quantifiable, and reproducible, and they have been tested in many variations of the original thought experiments that first brought them to attention. In this way, entanglement becomes a central feature of quantum physics, linking the behavior of separated systems through their shared preparation and providing a foundation for many of the more complex phenomena that arise when large numbers of quantum components interact. In the laboratory, entanglement is not only a theoretical construction, but a measurable and controllable feature of physical systems. To create and study entangled states, experimenters design setups in which pairs or groups of particles are produced together in well-defined ways, then sent to separate detectors where their properties are measured under varied conditions. The patterns in the resulting data show whether the systems share correlations that cannot be explained by assigning independent properties to each part. These experiments require careful attention to sources, timing, alignment, and isolation from disturbances, because the quantum links represented by entanglement can be fragile when exposed to uncontrolled interactions. One widely used method for generating entangled particles involves light. In a crystal with suitable properties, an incoming photon from a laser can sometimes convert into a pair of lower energy photons in a process known as parametric down conversion. Energy and momentum are conserved in this process, and the two outgoing photons leave the crystal in correlated directions with correlated polarization properties. By selecting particular directions with optical elements such as lenses and apertures, and by filtering the light to choose a narrow range of energies, experimenters can isolate pairs of photons that are prepared in a joint polarization state that is entangled. In such a state, measurements of polarization along certain directions yield strongly linked outcomes, even though each individual result appears random when viewed in isolation. The experimental setup in these photon experiments typically includes a source and arrangement of optical components to split and direct the light and 2 measurement stations placed at some distance from the source and from each other. Each station contains devices such as polarizers, wave plates, and detectors. The polarizers can be rotated to select different measurement directions for the polarization, while the detectors register whether a photon arrives in a channel corresponding to one result or the other. The stations are equipped with timing electronics that record the arrival times and outcomes so that detection events that belong to the same pair can be matched in the analysis. To test the specific predictions of quantum theory, the experimenters vary the settings of the measurement devices on each side and record the joint statistics of the outcomes. For each pair of settings, they count how often the results agree and how often they differ. From these counts, they compute quantities that in a broad class of classical models with local hidden variables must satisfy certain inequalities. Quantum theory predicts that for entangled states in suitably chosen settings, these inequalities are violated. When the experiments are run and enough data are collected, the computed quantities can be compared with the classical bounds and with the quantum predictions. Many such experiments using different implementations and improvements have found results that agree with the quantum values and exceed the classical limits by significant margins. Achieving reliable conclusions in these tests requires closing various potential loopholes. For example, if detectors fail to register some fraction of the incoming photons, one must ensure that the subset of detected events is not biased in a way that could mimic quantum correlations. This leads to the use of detectors with high efficiency and careful calibration. Another concern is that signals or influences could, in principle, travel between the measurement stations and coordinate the outcomes in a classical way. To address this, the measurement choices on each side are made rapidly and randomly, sometimes while the photons are already on their way and the stations are placed far enough apart that according to the usual limits on signal speeds, no influence could travel between them in time to affect the results. By combining high detection efficiencies, fast and random setting choices, and sufficient separation, modern experiments reduce alternative explanations and strengthen the case that the observed correlations reflect genuine entanglement as described by quantum theory. Entanglement is not restricted to light. Systems of trapped ions provide another platform where entangled states can be prepared, controlled, and measured with high precision. Ions held in electromagnetic traps can be cooled to very low motional energies by interacting with carefully tuned laser light. Their internal energy levels, which act effectively as two-state systems similar to spins, can be manipulated by additional laser pulses. Interactions between ions mediated by their shared motion in the trapping fields can be engineered so that the application of specific pulse sequences entangles their internal states. After preparation, the state of each ion can be measured by illuminating it with light that causes only one of the two internal states to fluoresce. Detectors then record whether each ion glows or remains dark. By repeating the experiment many times and varying the applied pulses and measurement bases, experimenters can reconstruct the joint statistics and verify that the ions occupy entangled states. Superconducting circuits offer yet another setting. In these systems, tiny loops of superconducting material interrupted by elements that allow tunneling of pairs of electrons form circuits with two dominant quantum states that differ in properties such as the direction of current flow. These states play the role of qubit levels. The circuits are cooled to temperatures near absolute zero to reduce thermal noise, and they are connected to microwave resonators that allow precise control and readout. By applying sequences of microwave pulses and using engineered couplings between nearby circuits, entangled states of multiple superconducting qubits can be generated. Measurements then reveal correlations in their outcomes that agree with quantum predictions for entangled systems. Solid-state spins in certain crystals, photons in optical fibers, and even collective excitations in cold atomic gases have all been used as carriers of entanglement in experiments. Despite the variety of platforms, the basic logic remains consistent. A controlled interaction prepares a joint state. Local measurements are made on each part, often with settings that can be changed between trials. The joint outcome statistics are recorded and compared with theoretical descriptions. When the data show patterns that cannot be produced by any model in which each part carries independent hidden properties unaffected by distant choices, entanglement is confirmed. Beyond testing fundamental principles, entanglement is also used as a tool in laboratory tasks. In quantum metrology, entangled states can improve the precision of measurements beyond what would be possible with uncorrelated systems for the same amount of resources. For example, entangled photons or atoms can be used in interferometers to measure small phase shifts more sensitively because the collective properties of the entangled state respond more sharply to changes. In quantum communication protocols, entangled pairs can be distributed between distant locations and used to establish correlations that assist in tasks such as secure key generation. In these applications, entanglement is treated not as an oddity, but as a resource that can be prepared, quantified, and consumed. The presence of entanglement can be assessed by various criteria, including whether experimental data violate Bell-type inequalities or whether certain mathematical measures of correlation exceed bounds that hold for separable states. As systems grow more complex, direct tests of Bell inequalities become more challenging. But other signatures, such as the ability to perform transformations that require non-classical correlations, indicate that entanglement is present. At the same time, it is observed that entanglement is sensitive to interactions with the environment. When entangled particles or qubits are exposed to uncontrolled noise or scattering, their joint state can gradually lose its non-classical correlations in a process often called decoherence. The outcomes of measurements then approach those that would be expected from a classical mixture of independent states. In the laboratory, considerable effort is devoted to isolating systems from noise or to correcting for its effects in order to preserve entanglement long enough to carry out intended experiments or operations. The study of how entanglement is created, distributed, and degraded provides insight into the boundary between microscopic and macroscopic behavior. It shows that the strong quantum correlations of entangled states are robust enough to be observed over large distances and in systems with many degrees of freedom, as long as interactions with the environment are controlled. At the same time, it illustrates how, in ordinary conditions where systems interact with many others in uncontrolled ways, these delicate correlations can quickly become unobservable. In this sense, entanglement experiments in carefully prepared settings offer a glimpse of structures that exist in principle more broadly but are usually hidden at everyday scales. Through these laboratory studies, entanglement is established as a real and measurable aspect of nature. The procedures for generating, manipulating, and detecting entangled states form an essential part of modern experimental physics. They provide both stringent tests of the quantum framework and practical tools for exploring new regimes of measurement and information processing. Building on the concepts of discrete events, superposition, uncertainty, and interference, these experiments confirm that quantum systems can share correlations that extend across space in ways that have no direct classical counterpart, while still respecting the overall constraints imposed by relativity and by the statistical structure of the theory.